In this module, we will introduce an approach to controller design. In the previous module, we gave a simple illustrative example of how to design a controller. In this module, we will try to be a little bit more rigorous. Specifically, we'll discuss how to generate requirements for a control system. Then we will introduce one particular approach to controller design, which is a pole placement approach. And finally, we'll introduce a controller structure that's the most prevalent in industry today, and that's the PID controller. So in general, engineers are familiar with the concept of developing requirements, quantifiable measures of whether or not the system performs to a certain level. With control requirements, there are typically specific types of requirements for control systems. Therefore, we must be able to take specifications on the larger system and translate them into specifications specifically on the control systems. For example, a vehicle may have a requirement on a 0 to 60 time, or something to do with passenger comfort, or different components may have a voltage rating or a current rating. And so we need to keep those in mind and translate those into controller specifications. Example specifications in terms of the transient performance of a control system often derive from the system's step response. So some of the things that we've discussed previously are things like time constant, which captured the speed of response of a system, in particular a first order system, overshoot, peak time, settle time, and rise time. And so these things capture sort of the speed of response of the system, as well as the amount of oscillation in the system and how quickly that oscillation damps out. Control systems often also have requirements on their steady state performance. For example, that the steady state error must be less than some amount for a particular type of input, a step input, a ramp input, or something more general. In order to test against this specification, we can apply the final value theorem for different types of reference inputs. And here is a reiteration of the final value theorem, in particular for error. Throughout the course of this semester, we've learned that the poles of a system or its transfer function are an indication of its time response, its natural response. So one approach to controller design is to try and design your controller, choose your control gains so that the poles of the closed loop system meet the given requirements. That is, give you a certain speed of response, give you a certain overshoot, things like that. If a system is simple, a canonical first order or a canonical second order system, then we have precise relationships between poles and the shape of the step response. For example, we have an exact equation that tells us how peak time relates to the imaginary part of a pole, or if it's a first order system, how the pole relates to the time constant. If a system is more complicated, it's not a canonical system. For example, if it's a higher order system, these requirements or these expressions that we've derived won't hold exactly. But one idea with a higher order system is to place one or two dominant poles to meet the requirements and place the rest of the poles to be significantly faster, so that we can, in essence, neglect the effect on the dynamics or on the transient response. Similarly, if a system has a 0, it's again not canonical and our relationships don't hold exactly. However, we can still approximate the system as a canonical system and use these relationships we've developed to give an indication of the effect of poles on response, even if they're not exactly right. They give an indication of trends. And seeing that a lot of times these canonical relationships don't hold exactly, this process will often be iterative. We can use the relationships to sort of determine should we make the gain bigger or larger, but in order to know for sure, we'll actually have to sort of test it out and then go back and modify the gains.